So David did his PhD in planetary science and his postdoctoral work both at Caltech. He's now at JPL. He's been there since 2002. His interests are on the weather data analysis, modeling and forecast of the Martian atmosphere, orbital surface observations of the Mars atmosphere, and then long-term evolution of the climate change on the Martian atmosphere. So he's been involved in project work as well. So he's done support for the Mars Reconnaissance Orbiter and the Mars Science Laboratory. So, David?
Okay. And I should probably apologize to those of you that know anything about Mars, because I'm going to start off with some very basics here. So Mars is a terrestrial planet with a thin atmosphere. This is the same general classification as the Earth, and so there are many similarities, yet there are many differences. Here's an image of Mars, here's an image of Earth. I hope you recognize both of them. As you can see, there are many things that are very similar between them, but there are also some differences that jump out at you. The first difference is basically the size of it. While the sizes are different, it's interesting to note that Mars actually has more land surface than the Earth, primarily because it does not have any oceans on it, which is the second thing you will notice. It doesn't have any of the blue. It has no significant amounts of liquid water, perhaps even no liquid water at all at present. The size actually, in terms of the surface itself, doesn't have a huge impact because it primarily just affects the gravity, which is a second-order player in most things. Other things that are very similar is you'll notice that both have clouds on them, both have polar caps on them, water ice polar caps in both cases, and significant amounts. So there is significant amounts of water on Mars, it's not in the form of liquid. The Mars year lasts 668.6 sols. A sol is what we call a Martian day. It stands for solar day. A sol is slightly longer than an Earth day, but they are very similar, which actually means that things work out fairly well unless you're forced to live on Mars time for a long period, as certain rover drivers did. Mars' orbit is significantly more elliptical than the Earth's orbit. It has an ellipticity of 0.09, so it's not really very elliptical, but it is noticeably more. The primary impact of this is that it means that the insolation on Mars changes by about 45% over the year. So this is a very big driver in a lot of aspects of Mars, especially for the atmosphere, but also for the surface and for operating on the surface. We use what we call L sub s, which is the heliocentric longitude, to designate the season. Mars has an axial tilt that is very similar to the Earth. Again, there are many aspects that are similar, and so it has a similar type of seasonal system. We generally define 4 seasons named after the terrestrial seasons. We've got northern spring. This is the start of the Mars year. In this season, there's relatively little dust in the atmosphere, and so it is a cold and cloudy atmosphere overall during that season. Also, towards the end of this season is when Mars reaches its aphelion and furthest distance from the sun, and so it has the lowest insolation. Northern summer starts at L sub s 90. This is very similar to spring. It remains cold and cloudy, but towards the end of the season, you start to see a little bit of dust increase, and you start to see a warming as it's transitioning towards its next season in southern spring. I usually use southern spring, but other people prefer northern autumn. It depends on one's point of view and the focus. This is a season which is a transition. You've got a general increase in the dust in the atmosphere. You've usually got a much warmer atmosphere as the season evolves. And perihelion, when you're closest to the sun, is towards the end of the season at L sub s 250. That's when you get your maximum insolation, and because it is a southern spring, your maximum insolation is when your sun is close to its furthest south point, or about at 25 south. Southern summer then continues on, and it continues to be significantly dusty and generally warm atmosphere, although towards the end of the season it starts to cool off as you're transitioning back to your northern spring. So kind of a global view of the atmosphere. There are 2 really regimes. There's the southern spring and summer regime here, where you've got a warm atmosphere overall. This is basically what you see during that atmosphere. And then you've got your northern spring and summer season where it's much colder. And these are 20 to 25 K for a global average temperature difference between the 2 seasons. In addition to the kind of mid-latitude or equatorial temperatures, you then have the very different winter polar temperature structure here, where you've got a warming up in the lower to middle atmosphere and then very cold down near the surface. The Mars atmosphere is generally divided into 4 layers. There's a boundary layer at the surface, which for ISRU is probably the most interesting point because it's the area where you're working in. It's much deeper and much stronger than on Earth, with a convective boundary layer in most parts of Mars that can reach up to 10 kilometers in depth. On the nighttime surface, you get a very cold surface with an inversion very close to the surface, so that there's a lot of cooling right in the last 1 to 2 kilometers. Above the boundary layer is the lower atmosphere, then the middle atmosphere, and then not shown up here is the upper atmosphere. Mars has polar caps and frost, as I noted earlier, and these are a very important player in the overall weather. This here shows the southern hemisphere throughout the entire Mars year. The black line is the CO2 seasonal polar cap. On Mars, during the winter, CO2 condenses onto the surface. CO2 also snows out. That's what the red dots are. The white dots are then where the CO2 deposits, i.e. snowdrifts, have basically piled up in large-scale areas that we can see on the surface. Mars at the South Pole has a very small residual polar cap that sits there throughout the summer, but during the winter season it grows out to 50 south, so it's a very large seasonal polar cap of frost that develops. In addition to the CO2 polar cap that we see every year, we also have water ice frost. For example, this is a Viking Lander 2 image of water ice frost shortly after dawn on the surface that they saw. Most recently, we've found that the surface of Mars, parts of the surface of Mars, even at the equatorial regions, have CO2 frost on them every night, so that they get frosted at least during part of the year on a regular basis. This leads to an annual pressure cycle. As noted earlier, the mean surface pressure is about 610 pascals. When I say mean, basically what we do is we don't have a sea level to use as a reference, so what we do is we kind of take a mean equatorial elevation and call that a mean, and so the surface pressure there is about 610 pascals on average. However, because of the seasonal variability, what you get is a very strong variation in the surface pressure over the year. This is Viking Lander 2 in red, Viking Lander 1 in blue. The black individual dots are individual daily surface pressure averages, and then the curves are a low order fit to them, and you can see that you have 2 maximum and 2 minimum. These correspond to the seasonal caps at each pole growing out to their maximum extent. That's when we've got the minimum amount of atmosphere and the maximum amount of atmosphere in them. You will also notice that the 2 are offset. The altitudes of the 2 were somewhat different, and therefore we see a significant difference in surface pressure with altitude. Mars has extreme topography, as it was noted here, with about 28 kilometers of total elevation variation. The scale height, or where you see the temperature or the pressure change by factor of E, is about 11 kilometers, actually very similar to the Earth's value. And so between the lowest point, Hellas, and the very top of Olympus Mons, you get a factor of 13 in surface pressure just due to the altitude, which is much larger than you see on Earth. So it's something to take into consideration in terms of how much CO2. Yes, the average is 610 pascals, but the actual value you're working with may be significantly different depending on where you are and depending on the season you're at. You will also notice, looking in here, that towards the second half of the Mars year, you get a lot more variability day to day. This is due to the amount of dust, and then during a huge global dust storm, you see this very large excursion in surface pressure. So even if you are at a given location, your surface pressure will vary a lot, much more than even a hurricane varies the terrestrial surface pressure. As noted earlier, Mars is a place of extremes. Not only does it have extreme weather over an annual cycle, it also has extreme weather over a diurnal cycle. The diurnal surface pressure change on Mars is about 10%. This is huge compared to what we see on Earth. This here is for MSL. This is 35 days or 34 sols. And it going from blue to red, you can see the seasonal evolution, but superimposed on it, you can see the diurnal cycle here. This is over an entire day from midnight to midnight here. And you can see that there's this very large pressure deviation, which is similar but not identical day to day. There is weather on Mars. Likewise, the surface temperature shown down here, again over a diurnal cycle, this is at 4 different seasons throughout the Mars year from MSL, shows a very strong variation. You've got your nighttime cold temperature, your morning warming to your peak high temperature midday, then it cools off in the afternoon and throughout the night until you get back around the cycle. And this here, in this case, is about 60 to 70 K of variation. Places elsewhere on the surface, we routinely see 100 K of variation. So any system you've got sitting on the surface either has to heat itself or has to deal with this type of environmental variations that it's going to see. On the flip side, you can also use this environmental variation maybe because you're getting quite cold here. So maybe you can do some of that condensation that you wanted to do to make your liquefaction going on just by waiting to the right time of the day to move the gases through the system. I should note that local and regional topography plays a major role in the near surface and boundary layer. Basically, it influences your weather, much like on Earth, but to an even larger extreme. There's a thin atmosphere, a strong surface heating, and so you develop, as I said, a vigorous convective layer and a lot of winds around that. But on the other hand, because the atmosphere is so thin, the winds really don't have that much force in them. Composition, here is the current best composition of the atmosphere. It's, as we noted already, predominantly CO2 with a couple percent of argon, couple percent of nitrogen, a little bit of oxygen, and then a whole bunch of trace species. There's even more down here that are potential, that have been detected or have upper limits to them. A couple that are worth noting, first of all, is well, this is the nominal amount of CO2. Because you're freezing out so much of the atmosphere on the poles, there's actually significant variation in that number over the annual cycle. The second one is water. Water is incredibly variable on Mars. You can see here that it's varying by 2 orders of magnitude. The total amount of water is tiny. We measure water on Mars in what we call precipitable microns, i.e. if you condense all the water out on Mars onto the surface, you get a few tens of microns to maybe 100 microns worth of water layer. That's it from the atmosphere at best. So most of the atmosphere is incredibly dry, primarily because it's very cold. I just put them up here because I had them, but the various isotopic ratios, some of them are quite different from the Earth, especially things like argon and D to H. So if your process is sensitive to those type of isotopic ratios, you need to make sure that you're doing with it. One of the big players in the Mars atmosphere that is different from the terrestrial atmosphere is dust. Dust and dust storms are a key driver of the Martian weather and climate. You've heard me refer to dust before. Basically, dust in the atmosphere absorbs sunlight and heats it. Otherwise, the atmosphere is very cold. It's very efficient at heating the atmosphere because it's opaque over most of the wavelengths as opposed to the gas itself. This has the interesting impact, and especially in dust storms, of creating positive feedback cycles. You basically get the dust in the atmosphere, the dust absorbs the sunlight adds energy to the atmosphere. When you add energy to the atmosphere, you get faster winds lift more dust off the surface, and you can get into a positive feedback cycle. The dust is ubiquitous on Mars. It's in the atmosphere, it's sitting on the surface, and it's basically a fine-grained, light-tone component of the soil. It's got a composition similar to the standard basaltic Martian soil with some enrichments of sulfur, chlorine, and iron in it. Effective radius is order 1.5 microns. We assume it's a modified gamma distribution. We don't have very good information on the dust in terms of what exactly it looks like. This is assuming that it's more or less spherical particles, which it definitely is not. The background amount of dust in the atmosphere varies over the year. Like I noted earlier, this controls the temperature and affects variously how things behave over the Mars year in the atmosphere. Not only do we kind of have a layer of dust near the surface, but at many seasons we also have dust as high as 40 kilometers, and we frequently see dust layers in the 20 to 30 kilometer region. These are enhancements of dust in the lower and middle atmosphere that are just sitting there. This I should say is an image from high rise of a dust devil on the surface. These are very common. We see the tracks behind them. This particular one was particularly nice. It was captured in their image, and you can see the dust devil here, and you can see behind it the shadow. This one goes up to order 20 kilometers in height based on the shadow length. There's a diffuse top up here as well that's not as easy visible in this image. So this is kind of one of the ways the dust gets off the surface is through the dust devils. They're everywhere, just about at all the seasons, because we've got such a convective atmosphere, and so they're probably a significant player in just keeping the background amount of dust in the atmosphere. The other way that we get dust in the atmosphere are dust storms. Dust storms range on all scales. This is kind of what you would think of on Mars as a standard storm. You see them routinely. There is a dust storm going on just about all the time. They occur at all seasons. This image here is a local dust storm from Marcy data. Here you can see the dust storm very nicely. This is, I believe, along the northern polar seasonal cap up here. That's why it's whitish up on this side. This is a water ice cloud. We often see water ice clouds near and above the dust because the dust is a condensation nuclei for the water ice. Dust storms range on all scales. Local ones are small, a couple days, maybe 1,000 kilometers in diameter. They really only affect the atmosphere near them, but if you have one run over wherever you're sitting, you will notice it. Regional ones, 3 days to a few weeks. They can actually leave dust hazes in the atmosphere that persist and therefore decrease your sunlight for quite a while afterwards. These occur on a fairly regular basis. Then you get up to the larger ones, what we call large regional or planet encircling. These affect an entire hemisphere for a month or more. They can also have thermal effects on the atmosphere globally. Basically, they've gotten large enough that they're affecting the global circulation of Mars. Finally, the ones that are the real ones that we all think about are the global dust storms. These affect the entire atmosphere for a month to 3 months to perhaps even longer. They have essentially dust everywhere. The classic example is when Mariner 9 got there, and the only thing it could see on Mars was the tip top of the 4 tallest volcanoes. Everything else was an orange haze. And that lasted for months as that dust slowly settled back out of the atmosphere. The largest dust storms, fortunately, are confined to the southern spring and southern summer seasons. This is around perihelion when the planet's getting the most sunlight. We assume that this is tied together, although we don't really understand the dust storms very well, especially in terms of predicting exactly what they're going to occur. It's a process that we're working on understanding. So putting that all together, and if you're going to do solar-powered ISRU, what is the sunlight that you've got available to you? That depends where you're at. As 2 examples, here is MER A, or Spirit, at 14 south. Here is MER B, or Opportunity, at 2 south. In green is basically the power that they were generating from their solar panels. And you can see that it varies hugely for Spirit. You've got these massive changes in it. This is a combination of a number of factors. The first factor is just the distance to the sun and its latitude and where the sun is relative to it. And the second factor in blue is how much dust is there in the atmosphere, and you'll notice that this varies quite a bit. The dust, here is a peak during a global dust storm when you got almost 5, an column opacity of 5, i.e. the sun was barely, you couldn't really make out the disk of the sun itself from the rover. So that's another factor that strongly affects the amount of sunlight you get. Final factor is that solar panels have this problem that the dust settles on them. And the dust tends to stick to them. Not only does it settle on them, and thus this red line, which starts at 1, which is a perfectly clean set of panels, is how much dust is sitting on the panels. The lower it is, the more dust on it, and the less solar power you get from the rover. You can see here that it is, for Spirit, a fairly constant decrease throughout its life, but there are also jumps. These are events when you get local winds, dust devils that run across them that lift the dust back off. But they never lift it all the way back off to perfectly clean panels. And depending on what you're doing, you can get quite low here. This is down to 1/4 of the actual production is coming out of those panels at the minimum there, just due to the dust on the panels, sitting on the panels, not to mention the dust in the atmosphere and the distance to the sun. Opportunity shows a much more variable. It's at an equatorial site, so it's got a better insulation to it. It doesn't respond as strongly to the combination of the ellipticity and the location. So moving on to the surface of Mars, I should note that I'm not a surface scientist. I will try my best to answer your questions on it and give you a high-level overview. This is just Mars showing some of the major features. We will refer to them, and so for those of you that aren't familiar, I figured I should put a map in. A couple of the key ones are the Hellas Basin right here. This is the lowest point on Mars, a very large impact crater. Valles Marineris, the huge valley system on Mars. the Tharthus Montes and Olympus Mons. These are the 4 large volcanoes, a huge volcanic province, with the top of Olympus Mons being the highest point on the planet. This is shown here clearly in the topography. The topography of Mars is highly varied. There are a huge different number of terrains on it. For those of you that aren't familiar, we divide Mars's geologic history into 3 ages. We have the Noachian, which is the ancient age. This is mostly this cratered highland in the south that is the Noachian terrain. We have a Hesperian or intermediate age, and then we have an Amazonian, which is the recent terrain, which is primarily the northern plains up here, which are relatively low-lying. Note that when I say recent for the Amazonian, this covers several billion years. The Amazonian stretches, depending on who you want to talk to, 2.5 to 3.5 billion years. So it is a lot of the history of the planet when we're referring to Amazonian. We have the volcanic provinces here, which is the Tharsis Bulge. This is a huge volcanic complex on it. Looking at the surface, here are from rovers various views of the surface of Mars. And you can see that we've seen a broad variety of terrains as we've looked at Mars. We have these rocky terrains that were typical of Pathfinder, Viking landers. We've had the what we call the polygonal terrain. This is the icy terrain seen from Phoenix. We've had Spirit, which was a low rock terrain, but with some hills in it, and I didn't pick a picture with it, but some very interesting geology in those hills. Opportunity saw cliffs here. This is at the edge of Victoria Crater here, and then this very flat terrain on top that is very dark, that was very different from everything else we saw. And Final Curiosity has seen some interesting terrain. So there's a wide variety of terrains. However, we have not really, even with all the rovers and landers we've had, sampled much of the terrain of Mars. This is a map of thermal inertia on this scale, i.e. this is basically how much dust versus how much rock near the surface, and albedo, how dark and how bright it is. And looking at it, this is a contour map, and you can see that there's 3 areas, A, B, and C, that kind of where a lot of the terrain of Mars clusters. Mars A is very bright and very low thermal inertia, i.e. extremely dusty. We've never gone there or even close to them. This is the type of terrain that we really are afraid to land in. We don't know if we will sit on it and sink or what exactly will happen there. So we've never gone even close to that. B here is a terrain that is fairly dark and somewhat rocky, or not rocky depending on a particular location. Opportunity was in one of those very dark places, but it may have been a very unusual and not typical for them. But as you can see, most of our missions have landed right here in this C cluster, and so that's really the only one we've sampled. There's all this area out here as well. There aren't many terrains that are like that, but there are some, and they add up overall that we haven't seen at all. These are places where you've got rocks or perhaps even bedrocks or other things that might be interesting for mining that are actually quite hard to go to. As was noted earlier, there is water ice on Mars, and this is a measurement of the amount of hydrogen that's been detected. So this is a detection of either hydrogen or of either water ice, or it could be hydrated minerals. The polar regions have a lot of hydrogen in them. There's water ice close to the surface or at the surface at the actual North Pole. You can also see these regions here, which are more highly hydrated minerals in the equatorial areas, probably. Superimposed on this is one of the things that has come up in the last few years as a new feature that we weren't really thinking of, are impact craters. All the black dots, all the little dots are impact craters, black ones, white ones, and blue ones. What is interesting is that some of them, when we look at them right after they form, have very bright spots around them. And when we've looked at them with a spectrometer, we've seen that it's water ice. It is very pure water ice that is coming up from these craters. These are tiny craters. They're meters to tens of meters in diameter. So they're only excavating meter to a few meters into the depth, and they're bringing up almost pure water ice. Most of these are in areas where we see water ice, where we've seen water ice in the past from orbit, but some of them are not. So there's a little bit lower than the gamma ray spectrometer can penetrate. It can only penetrate very shallowly into the depth. There's probably more ice here down at 1 meter or 2 meters in some of these places. And so we're using these craters to map it out. You'll notice that the locations of the craters is very non-uniform. We can only find the craters in the areas where there is dust on the surface, so that when they hit and they create a blast zone, that the low resolution cameras that are the ones that can search over large areas of Mars can find them easily. So we have to be careful to remember that there are biases in our sampling. And for example, if you look, there's very, very few down here in this cratered terrain. And we'd really love to know where this boundary is and where there is and isn't ice yet, but it's hard to find the craters to do that. Aqueous minerals, as we noted, are a potential source of ISRU materials. We have seen a lot of different minerals. Some of them are indications of past aqueous activity. Some of them have significant water in them. And we see them in quite large areas of the planet. They are somewhat all over. However, most of these detections are very small. One of the issues with spectrometer detections is most of the surface of Mars is dusty. And so all you see is dust. Each one of these little spots is probably 10 times smaller than the actual dot put on the maps that you can see, what was the detection. So there's a lot of it there, but we have a hard time knowing, is it continuous or is it just little discrete packets that we have to go to, and how do we deal with that? So that's one of the challenges going forward in terms of the surface of Mars, is if you don't want ice, which is in the polar regions, and one of the problems with going to the polar regions, I mean, the obvious answer is if you want water ice, just go to there and get ice. You can get plenty of it. The problem is then you have to figure out how do you deal with getting yourself covered in several meters of CO2 snow during the winter and frost. And is that really what you want your ISRU system to be working, sitting at 130 K in CO2 frost? So coming back to it, here is Mars and the Earth, two similar, two different planets. I hope I've helped you understand some of the similarities and differences between Mars and the Earth. So thank you. I'll leave it at that and take questions.